The electric charge. But what is the electric charge? It's the current stuff? The plus and minus stuff? Who knows? The correct answer is who knows. Saying what electric charge actually is, it's very complicated and nobody really knows the answer. Electric charge is a property of matter and there's not much more to say about it. There are two factions within the electric charge, positive charge and negative charge. The boss of negative charge is the electron, because in nature there are no particles with charge smaller than the electron. Minus 1.602 times 10 to the power of minus 19 coulombs. On the other side there is the proton, with the same charge as the electron but positive. Neither can win over the other. Their charges are identical, but the proton is bigger than the electron. And when I say bigger, I mean bigger. The electron mass is 9.11 times 10 to the power of minus 31 kilograms, while the proton mass is about 1800 times larger, 1.67 times 10 to the power of minus 27 kilograms. And speaking about charges, we all know one thing. Charges with opposite signs attract each other. Charges with the same sign repel each other. Like my cousins, Bortolo and Rocco. Bortolo lives in the mountains and he cuts trees with his hands for a living, while Rocco lives near the beach and he's a lifeguard for fishes. When vacation time comes, Bortolo just wants to escape his rocks and woods. The only thing that really attracts him is a white beach and the chemical smell of sunscreen. Rocco, on the other hand, sees enough water and sand during the year. What really attracts him are mountains and a good spretzel dish. Same story goes for electric charges. But exactly why do electric charges attract each other? I mean, if these two guys are not even close, how do they know that there is another charge in the area? Like when you're watching memes in your room and your mother on the other side of the house calls you because dinner is served! The ancient call will get you up and make you run to the kitchen, without your mother having to physically come to get you out of bed. But electric charges are not able to shout that dinner is ready, so there must be something else underneath that makes them move. What we might consider as the voice of electric charges is called the electric field. If this name does not sound new to you, nothing strange. Either you have recently seen a Norse god shooting lightnings in the middle of a field, or you have remembered that you have already encountered the word field, to be precise, when you studied gravity. It's exactly the same concept. If you need to refresh your memories, go and watch our amazing video about the gravitational field. The electric field is a deformation of space produced by the presence of a charge. Positive electrical charges create a hill-like deformation of space, like this, while negative charges create holes, just like Bortolo who lives in the mountains and Rocco who lives by the sea. Positive charges, like Bortolo, tend to go towards the sea, so towards the pits of our electric field, while negative charges, like Rocco, tend to go up, climbing the electric field. This is the electric field, and this is why charges move. The electric field simply tells charges which way to move, depending on their sign. Also, larger charges will create larger deformations, and if you distribute many charges in different ways, you can create very different field shapes. Matteo, nice geography lesson, but I still don't get what this electric field is. If you want to visualize the electric field in another way, you can use field lines. Field lines are arrows that show the direction of the deformation caused by charges. The rule is simple. Field lines always go from top to bottom, so they always come out of positive charges and go towards negative charges. If you place a positive charge anywhere in space, it's gonna follow the field line it stands on, going towards the nearest hole, while a negative charge is gonna go up the field line and climb the first mountain it encounters. Wait a second, Matteo. Those arrows. Is the electric field made up of Vectors? Yep, that's right. The electric field is a vector. Since it must show charges which way to move, it's important that it provides a direction and a sense. You can think about it this way. At each point along the field line, there is a sign with an arrow. That sign is the electric field at that precise point in space. If an electric charge shows up at that point, if it is positive, it will simply go in the direction shown by the sign, while if it is negative, it will say, "F the system!" and it will go the opposite way. The stronger the electric field, the faster the charge will move. To give you a more mathematical definition, a field is a function that associates a vector to each point in space, or if you prefer, it associates three values, which are the three components of the vector. If a charge is in a place where there is an electric field, there is a very simple formula that tells you the force that will make the charge move. Force equals electric field times the value of the charge. But please be careful, the electric field here is not the electric field generated by the charge Q. It's another field that was already there, produced by the environment around the charge Q. Okay, Matteo, but how do I figure out the magnitude of the electric field? I just can't figure it out by myself. That's the point. The electric field formula depends on the situation. As we have seen before, the shape of the electric field depends on how charges are arranged in space. So the formula to calculate it also depends on what charge configuration you have. I mean, they are electric charges nonetheless, but if you spread them differently, you get different fields. It's like saying that with your guitar you can play different songs, even if the instrument is always the same. But now, math! Number 1. The electric field produced by a single point charge is 1 over 4 pi epsilon 0 times the charge, unsigned, divided by the square of the distance of the charge from the point where you are evaluating the electric field. Epsilon 0 is called vacuum permittivity and it is 8.85 times 10 to the minus 12 Coulomb squared over Newton times meter squared. If by chance your electric charge is not in the cosmic vacuum but is immersed in another material, such as water, air, meatballs, you must add an epsilon r down here. Epsilon r is called relative static permittivity and its value changes according to the material. So for example, if you have a charge of 2 coulombs and you put yourself 5 centimeters away from it, its electric field will have value 1 over 4 pi times 8.85 times 10 to the minus 12 times 2 divided by 0.05 squared newtons over coulombs. That is 7.11 times 10 to the power of 12 newtons over coulomb, and the vector will point away from the charge because it is positive. If instead we put ourselves 4 kilometers away, the electric field will be 1.11 times 10 to the power of 3 newtons over coulombs, and again the field is going to point away from the charge. Long story short, the field of a point charge has a radial shape, like the rays of the sun, and this is the formula. For positive charges, lines go outwards, for negative charges, lines go inwards. Number 2. If you don't have a point charge, but a charged sphere, as long as you stay outside of the sphere, the electric field formula is the same as the point charge. The charge Q that appears in this formula is simply the total charge present in the sphere, while r is the distance from the center of the sphere. If, on the other hand, you are inside of the sphere, you have two possibilities. If the sphere is made of conductive material, the field is simply zero, because charges are distributed only on the surface of the sphere. If, on the other hand, the sphere is homogeneously charged, therefore it is made of the electric material, the formula is the usual 1 over 4 pi epsilon 0 times the total charge of the sphere divided by the cube of the radius of the sphere times the distance from the center. Even in this case, though, the electric field is always radial and points outwards if the charge is positive and inwards if the charge is negative. Number 3. If you happen to have a uniformly charged flat surface, Lucky you! In this case, the electric field has the simplest formula of all, sigma divided by 2 epsilon 0, possibly epsilon r. Sigma is called surface charge density, that is, the ratio between the charge on your plate and its surface. The good thing is that in this case, the electric field has the same value everywhere, regardless of the distance from the plate. As for the shape of the field, if the charge of the surface is positive, the field lines are straight parallel lines coming out from the plate perpendicularly. If the charge is negative, they are parallel lines entering the surface. Number 4. What if you have not one, but 2 plates? This is a very common situation, especially when dealing with capacitors. If these 2 plates have the same charge, but one is positive and one is negative, the formula is identical to the previous case, but without the 2 below. Sigma in this case is the surface charge density of one of the 2 plates. But be careful, this formula only works while you stay between the plates. In outer space, the electric field is simply 0. Its shape is the same as in single plates, perpendicular to the surface, coming out of the positive plate and going in the negative one. Number 5. If charge is distributed along a wire, the electric field is 1 over 2 pi epsilon 0 times lambda divided by r. Lambda is the linear charge density, that is, the ratio between the charge in the wire and its length, while r is the distance from the wire at which you are calculating the field. The field is radial and perpendicular to the wire, always pointing outwards if charges are positive and inwards if charges are negative. Number 6. There's just one more situation where you can find a reasonable formula, and that's when you are very close to the surface of a conductive material. Regardless of its shape, its field is sigma divided by epsilon 0 and or epsilon r, just like the 2 plates. The problem is that sometimes knowing sigma is not that easy here. But still, near the surface, the field is perpendicular and pointing outwards for positive charges and perpendicular and pointing inwards for negative charges. And now, the moment you've all been waiting for, a barking cat. I mean an example. An electron is wandering through cosmic nothingness. Then suddenly a metal sphere appears in front of it, charged with 12 microcoulombs with a radius of 100 meters. If the electron is 2400 meters from the surface of the sphere, what force is it feeling? To know the answer, we have to use the universal formula F equals Q times E. The force that the electron is feeling is equal to its charge times the electric field of the sphere. Be careful, this is not the electric field of the electron itself. The charge of the electron is 1.602 times 10 to the power of minus 19 coulombs, while the electric field produced by the sphere is calculated with the formula 1 over 4 pi epsilon 0 times 12 microcoulombs divided by the square of the distance between the electron and the center of the sphere, so 2.77 times 10 to the power of minus 21 newtons. This force is going to be directed towards the sphere because the electron is attracted by the positive charge. Now, however, let's complicate our lives a little bit. In addition to the evil sphere, there is also a huge negatively charged plate, with a charge density of minus 4 times 10 to the power of minus 12 coulombs over meter squared. What is now going to be the force felt by our poor electron? Well, in this case, in addition to the previous force, we have to deal with the force produced by the plate, which, being negative, will repel the electron in this direction. To calculate this new force, we always use F equals Q times E. This time E will be the field of the plate, sigma divided by 2 epsilon 0. The force we get is then 3.62 times 10 to the power of minus 20 newtons. The total force will then be easy. I add this force here to the sphere force and that's it. Burn in hell, you moron! Forces are vectors. You have to use different rules. In this case, since the two forces are perpendicular, their sum is the square root of the first one squared plus the second one squared, so 3.63 times 10 to the power of minus 20 newtons. I can hear you, morons. Yes, those of you who... Matteo, but why haven't you talked about Coulomb's law? I am subscribed, I hate you, boo! Guys, Coulomb's law is just a specific case of the formula F equals Q times E. If you take the electric field produced by a point charge and you place it here, you get the electric force between 2 point charges. That is called Coulomb's law. If your book spends half a chapter talking about this formula, it's just because it's the most common and simple case of attraction between charges. But this stuff here only works between 2 point charges. With balls, plates, wires and spiked clubs, the only thing that really works are the formulas we have seen together. If you find our videos helpful, please consider supporting us with a tip. You can find the link in the description below. And subscribe! A huge thank you to all our supporters, you make this possible. In the meantime, take a look at the other lessons and we'll see you next time. Ciao!